Maybe remind you where we ended last time. So.
I like the way that these lectures, like, I don't like. The difference, like, the question on this, or like. There was. Oh, wow.
Okay, so what happened what we were discussing last time is that if you have a function of two variables, you can find its gradient. Remember that the gradient is just a vector of partial derivatives. Okay, so again, the gradient changes from point to point. So I'm just drawing the gradient at a particular point, but maybe some here, like the gradient could look like this, and then the gradient could be like this other vector and this other vector. So this vector can that I'm drawing there is not necessarily constant, right? It will depend on x and y in general. And then if you're given a particular direction in space, and say you wanted to know how much the function, like what's the rate of change of the function in that direction, that was a directional derivative, and the formula that I gave you last time is that it is the dot product between the gradient and the vector v. Okay, and so that is the length, that is the length of or the magnitude of the gradient times the magnitude of v times the cosine of the angle between them. The thing that I mentioned near the end of the class is that for like it's a convenient convention to have like the magnitude of the direction to be one. And so that way you end up with the formula for the directional derivative being the magnitude of the gradient times the cosine of the angle. Okay. Now, the point is that, again, this is supposed to tell you how fast or what the derivative in any direction that you choose on the plane, right? So since it depends on the angle or the cosine of the angle, and we know that the cosine is always between -1 and 1, that immediately tells you how big this derivative can become or how small it can become. So this is what I was writing at the end of last time, how big can this product be when the cosine becomes 1? So the maximum rate of change is going to be, so this is going to be the maximum rate of change, which happens when the cosine of theta equals 1. And when is that? That is when the gradient and the direction are parallel. So that occurs when both vectors kind of look like this. So maybe the gradient is pointing this way, and then the direction that you choose is pointing in the same direction as the gradient. So that's the parallel case. Then how small or like what's the most negative this can become? That's another way to think about it. That occurs when the cosine is -1. But when the cosine becomes -1, you get minus the magnitude of the gradient, and that's the minimum rate of change. Or if you want the maximum decrease, if you prefer to think about it that way. So and that makes sense in like if you have to walk this way to increase your temperature as rapidly as possible, then you just turn like the other way and that will decrease the temperature as rapidly as possible. So the direction that you have to choose here is like minus the direction of the gradient. So in this case, the direction of the vector V is like opposite to the gradient. Meaning that there's like a 180-degree angle, where the angle is 5 radians. Okay. And another important, so those are kind of like the extreme situations, how big it can get, the rate of change, how small or how negative the rate of change can become. And then there's like kind of like this intermediate case, which is also useful, which is when what happens when they're perpendicular, the direction that you choose and the gradient. So this last case, let me put it in a different color. It really is kind of like in between these two, but let me put it here. Is when you just get 0. And this happens when the cosine or they are at 90 degrees, right? So maybe now the gradient looks like this. And the direction looks like this. So they are at a 90-degree angle. Is that making sense? That was basically the last thing I mentioned last time. So how is this related to level curves, which is the other thing I was mentioning, and then I'll show you this animation again. So if you recall, the point of a level curve is that is when the function takes like a constant value. So let's just draw here like a level curve for the function. Uh, Let me see what I should do. Let's put it like this. Oh, let me use the orange. So this could be like a level curve. So maybe this is like the level curve where f equals 5 or 3, any number that you want. So let me just put f of x comma y equals like a constant. Okay. As a curve, it has tangent vectors, right? Any curve has like a tangent line. So there are like certain vectors that give you the direction of the curve. Or maybe the tangent vectors could look like this, right? So all these are represent possible directions on, you know, for the tangent lines to the curve. So obviously, like they're not the same vector, like they're changing from, they're potentially different, but I'm not going to call them use different letters because I would run out of them quickly. So I'm just saying like any of these vectors V represents like a direction to the curve. And the idea is that if you walk along a level curve, if you think about it kind of like as a path that you can walk along, then the point of the level curve is that the function remains constant. So if you just like stick to walking along a level curve, your rate of change is 0. It's like the function is literally frozen, right? Like that's the point of a level curve. There, you don't experience any changes in the value of the function. So if you want to think about if you want to think about the function like as temperature, which is useful, like if you walk along this level curve, the temperature is always 30 degrees or 50 degrees or whatever. So the rate of change has to be 0. And so that means that the directional derivative along these directions vanishes. It is 0. So in other words, the gradient, because of what we were saying in here, the gradient actually ends up being a vector perpendicular to the level curve. So that's kind of like a very nice property about the gradient. So here's like a perpendicular vector. Here's another perpendicular vector. Okay, so I'm drawing them kind of pointing away, like from the origin, like that's not, it could have pointed like this way. Like it's not obvious from what I'm saying, whether it would point in or out of the curve. That's less important. The important thing is like, it has to be like a vector perpendicular to the curve. So like I'll just draw it like in both ways, so to just emphasize that, it has to, has to be perpendicular, whether it points towards the inside of the curve or the outside of the curve actually depends on the specifics of what the function is. So you shouldn't read too much into whether like if it's inside or outside. The important thing is that the angle is 90 degrees. Okay, so the key fact or one of the really important facts about the gradient is that the gradient vector is perpendicular to like the level curves of a function. So gradient vector or is orthogonal. Does that make sense? Questions and comments about it? Let me show you the animation from last time, and then I'll tell you how we're going to use this. Because it's not super obvious what's the idea of like doing this, but I'll tell you like the main application of about that today. Yeah.
So what do the red arrows represent?
So, oh, I should have labeled them, sorry. Like that would be the gradient of the function. Yeah, thanks. This is the gradient. So, right, again, like it may not be obvious from the picture, you shouldn't like infer whether you should be pointing towards the inside or the outside of the curve, but at least being the gradient, it definitely needs to be perpendicular to the curve. That's the like most important thing of what I said. So let me see if I can show you the animation, and then I'll tell you like the main application that we have in mind for this. Oops. So, okay, this looks fine over. Let me see if I can fix it. Okay, now it looks better. So again, on the right-hand side, you're seeing the graph of the function of two variables. So the graph looks like some sort of surface. So a level curve like represents like if you think about it as a terrain, it will represent the values where the height is constant, right? So in this case, it's kind of like walking along this curve, right? On the mountain. The thing is like the level curves never get drawn on the graph itself. We just redraw them on the XY plane. Um, so that's like what this curve corresponds to. So I don't know if you see it here in yellow, but like that would be the level curve. Okay, and the black vector represents the gradient. In this particular case, it is pointing towards the interior of the curve because the top happens to lie inside this curve, and the gradient is always trying to point you in the direction of like the maximum value. So since the maximum value happens to be inside the curve, that's where the gradient is pointing. If you had turned like the mountain upside down, right, like then the the bottom of the graph would have been on the inside, so the gradients would have like pointing away from it. So what I'm trying to say is that if there's like you can move this dot along I'm trying to move along the level curve, and if you see like hopefully it's clear that the gradient arrow, which is the black one, is kind of trying to keep itself perpendicular to the curve. So that is what's happening here. Okay, is that making sense? And so that's kind of the idea of this report. So let's see. So what are we, let me do like a quick example for two variables. And then I'll do like the one I'm really interested in, but at least yeah, like I think like the first example would give you like a better idea of what's going on. So let me hide this. So just a quick application, which is kind of like the graph that was being shown there. So like, let's say you have like a function like 1 minus x squared minus y squared. If you look at that function, like the graph looks like that inverted salad bowl, because it is kind of like z equals 1 minus x squared minus y squared. So the graph of the function looks like this. So this is the graph. Right, and so from here you can see, you can kind of see that the level curves will be some sort of like circles. So what are the level curves? Level curves are obtained by setting the function equal to a constant. So to not give it any particular value, let me just call that c for constant. And so you get 1 minus x squared minus y squared equals c. And then like this is 1 minus c equals x squared plus y squared. And so the like the level curves are like just circles center at the origin of radius root of 1 minus c. So right? So that is what the level curves are here. And if you look at the gradient of this function, right? What is it? So again, like this function is 1 minus x squared minus y squared. And so the gradient of this function is kind of easy to find, because the partial derivative with respect to x is just minus 2x. So you get minus 2x comma minus 2y. Okay. And if you were to draw that, oh, in fact, we can, I will show it to you in a second, also on GeoGebra. But if what this is saying is that one way to think about it is that if you have a point x comma y, the vector that you're supposed to draw here is negative 2x minus negative 2y, and it's kind of like easy to like, oops, like it looks a little bit ugly. So it's kind of easy to convince yourself that that one is like a radial vector pointing towards the origin. Actually, of mine, like it's twice as big as the position vector, so I should probably draw it a bit longer. But the only thing that I want to kind of point out here is like the vector happens to be pointing towards the interior, because the interior is where at the origin is where the max occurs. And the other thing is that it's perpendicular to these circles. Okay, so all of these represent the gradient again. Does that make sense? Questions about it? So I posted like a video for you to watch on Grayscope about this gradient descent method, which has some applications to machine learning and other things, which is kind of like a fun video if you want to watch it, and then like you'll see how this idea can be used in other things. So just to show you the vector field before moving to the next situation. Oops. Let me even bring down. Right, if you just enter negative 2x minus 2y as the entries of the vector field, yeah, you'll see that this one is, like a, let me see if I can increase it. You'll see like this is like a radial vector field pointing towards, towards the interior, towards the origin. Uh, From the, from the coordinate system. Okay, so that's kind of how it looks like. And then all these arrows are perpendicular to like the consent, like the circle's center of the origin, which are the level curves for that function. Okay, so how are we going to use this? So the main application that we're going to use this for is to find equations of the tangent plane to a surface. So let me see if I can explain this now. So let's talk about in order to do that, I just have to tell you a few things about functions of three variables. But the good thing is that you'll notice that it's essentially what we have been doing so far. But there's like just like an extra variable to take care of. Okay, so like for this is basically what you would imagine, like a function that just happens to depend on x, y, z. Like just like start writing your favorite things and like would define write like a formula in terms of x, y, z, and like would define like a function of three variables. So that's like an example. That's another example, and just to put one more. So all of this would be like functions of three variables. And now the idea is that, so a couple of things that you want to say about this. Since like now the independent variables are x, y, z, if you have been keeping track of the analogy, I'm sorry, let me put them like. So when it's like a function of one variable, so here's a like analogy in terms of notation. When it's a function of one variable, you write something like y equals f of x. When it's a function of two variables, you write something like z equals f of x comma y, right? And then for a function of three variables, right, where you have f of x comma y comma z, well, you want to kind of set it equal to a new variable, which you typically just call w. So you would write something like w equals f of x, y, z. Why am I bringing this up? Because if you think of the xy plane, then the graph of a function of one variable is a curve, right? And then when you have a function of two variables, which is what we have been discussing so far in this course, like the graph looks like the surface, right? And then just by analogy, what would you need in this case? Like, so if you notice, like, as you increase the number of variables, you're increasing the number of axes, right? So x, y, then x, y, z, then what would you like you would need if you wanted to see the graph of a function of three variables is like x, y, z, w, right? That issue quotes is that you cannot really draw that in space because that requires like a fourth dimension, if that makes sense. So you're trying to put something like X, Y, Z, W, right? The thing is like this W axis has to be perpendicular to all of the original three, which cannot be done in space, like in three dimensions. So you cannot like, this is all to say that you cannot really visualize the graph of the function of three variables because the graph would live in four dimensions. That's what I'm trying to say. So the graph or can be plotted or requires four dimensions, requires an extra dimension of space. Is that making sense? So far so good. So when you have a function of three variables, the goal is not necessarily to graph it or like trying to understand what the graph is like, because that would require like more space than the actual space that we have. Like it requires more like dimensions. But still, there are like things you can do. So for example, you can still take partial derivatives in exactly the same way as before. So say, what would be the partial derivative of f with respect to x in this case? That would just be y. What is the partial derivative of f with respect to y in this case? That's just x. And what's the partial derivative of f with respect to z? That's just 2z. Okay, so the partial derivative still can be computed in exactly the same way, because the only thing that you need to find a partial derivative is to, pretend that the other variables are constant and take an ordinary derivative. And for that, you don't really need to like visualize anything. It's completely like algebraic. And well, let me just finish the others. Like, so what's the derivative with respect to x in this case? Is just z. The derivative with respect to y is 2y. The derivative with respect to z would be x minus sine of z. And what are the derivatives here? With respect to x, you get y. With respect to y, you get x minus z. And with respect to z, you get minus y plus 3z squared. Right, is that okay? Are all of those making sense? Now, that, like, it's still, you can still make sense of what all of these derivatives mean. So like, again, it is convenient to think about this function like some sort of temperature. It's just that before, when the function was of two variables, you were like, you were thinking of maybe this function as the temperature at the point x comma y. Now you could think of these functions as the temperature at a point x, y, z in space. Okay. So like now it's kind of like a temperature distribution, like in three dimensions. And then, so this would tell you how much is the temperature changing when you only change the x variable, fixing y and z, how much the temperature is changing when you only vary the y variable and things like that. So it's still, it's still rates of change, you still have like the same interpretation. It's just that you can no longer see the graph of the temperature function, for example, but the derivatives would still have like a similar meaning. You're just asking what's the rate of change of the function, when you move parallel to the x-axis or like y-axis or z-axis, if that makes sense. And then, so well, the first thing is just to kind of emphasize that the derivatives, to find them is exactly the same. There's not really any new difficulties here to find partial derivatives. And you can still kind of come up with the version of the gradient. So what was the gradient? Let me write it here as well. But what should be the gradient in this case? Should it just be like the partial with respect to x, comma, partial with respect to y, comma, partial with respect to z? So the gradient, like, it's just like all the possible partial derivatives. So. Or if you prefer in. So for like the gradient is essentially the three derivatives we just found, just like assembled as a vector. So it's this one. Oh, this is this. The other one would be c 2y x minus c. And the other one, the last gradient would be y x minus z minus y plus 3c squared. Is that okay? Is that making sense so far so good? Um. And still, they would look similar to how I was representing them last time. So let me show you how that looks. Here it is. Okay, so let me show you like some of these. Like again, you can just enter vector fields on the algebra, and then there's this useful animation. For like plotting 3D vector fields, it's just that this is like the first entry of the vector, second entry of the vector, and third entry of the vector. So for example, the first gradient was y x to z. So I'll put here y x to z. Let's see what we get. X to z. Okay, and that's how the gradient would look like in this situation. And unfortunately, I cannot rotate it. That would have been nicer, but I can make it smaller, the scale. So now in this case, it is a bunch of vectors in 3 dimensions. So like there are different ways to think about it. If you prefer like more physically, you could think about it as being like, again, like this, the velocity of the wind or like of a fluid in like, you know, in 3D, things of that it could also be like kind of like an electric field or like a magnetic field, things like that. So like there are a bunch of different physical interpretations that you could make. And just to put like the other, like the second one, just to show it to you, like it was z to y, x minus sine of z. So z to y. Let's see if this one can be shown. I don't know because it has a sign. So okay, yeah. So this is a different one. Okay. So you know, depending like of the function that you have, you can find like you have a function of 3 variables. You can compute its gradient, and then that you get like some vector field in 3 dimensions. Okay, so everything that we have been doing so far for 2 variables more or less work in exactly the same way when there are 3 variables around. So far so good. It's making sense to this point. So why? So how are we going to use this? The thing about what makes the gradient, one of the things that is interesting about the gradient when the function has dependent on 2 variables is the thing that I told you at the beginning of the class, that the gradient is perpendicular to the left curves, right? So we just have to find the analog of that in this case and see what that means. So for that, we have to think first of what it means to set the function equal to a constant. when the function is a function of two variables, and that would be like a level surface. So let's just talk about level surfaces first. The level surface is just what you get by setting the function equal to a constant, but now the function depends on three variables. Is an equation of the form f of x y z equals constant. So now you have a function of three variables, and you are asking, where does this function take the same value? And that will give you, instead of giving you a curve, it gives you a surface. So let me just draw like a random, like a generic picture, and then I'll do it like for specific examples so that you can see what I mean. So here's okay, so let's do some examples. So if f y z is like x squared plus y squared plus z squared, right? Like that's a function of three variables. What are the level surfaces of this function? They are what you, those are like the surfaces that you get by setting the function equal to a constant. So you set f equal to a constant, which I'll call z for constant, and so you get x squared plus y squared plus z squared equals c. And that's what is it? That's the equation of a radius. Sorry, of a sphere radius root of z. So these are just like spheres. Right, so the levels are depending on the value that you give to the constant, you get the spheres of different radii. I won't try to make too many because it gets like a bit messy, the picture, but hopefully you get my point that like, what, like again, if you think about it, about this as temperature, what this is saying is like, this is the temperature at a point X, Y, Z in space. And if you move on the surface of this sphere, then the temperature remains constant. Here's a different example. Let's say. Okay, what is that? There's a function of three variables, you set it equal to a constant. So you get z minus root of x squared plus y squared equals the number c, and that is the same as So this is one of the reasons that at the beginning of the class, we kind of did a small detour into those basic quadratic equations and their how they look like. If there's no C here, hopefully you recognize this equation. It's kind of like the equation of a cone. And so this is kind of like a cone translated by a certain amount. So like the level surfaces here are just cones. So these are just cones. So again, they're cones of different sizes. So it's hard to draw too many without like, maybe I should just draw one. Here, like it starts at height C. So depending on the value of C, you get different cones. And then just to do one more, hopefully to convince you to get surfaces. But before I move on, my point is that you cannot look at the graph of this thing. The graph we cannot see. The graph, because the graph would require like an extra variable, a fourth axis. Okay. So that is not possible to represent. You know, therefore, like it is analogous sometimes, like, to like when you have like a function of x, y, z, t, where t is time, right? So that like, where like, you cannot, like, if you wanted to plot like, space, what people call space time, you need x, y, z plus t, so you need four dimensions. And that you cannot really visualize, although you can do partial visualizations like of this sort to get some idea of what's going on, but that's still not quite the same. So, I mean, just like the last one. Okay, this one is nice actually. What are the level curves in this case? The level curves are x plus 3y minus z equals a constant. Okay, hopefully everyone should recognize this equation. What is this equation? A plane, right? That's just a plane. And the different values for the constant, they just shift the plane where it's drawn, but it's kind of like pointing in the same direction. Now, this one is a bit more interesting and maybe you'll see with this example where I'm getting at, because okay, hopefully this one is easy to like notice directly. What would be the gradient? Anyone wants to tell me what is the gradient of this function of three variables? Again, it's just like the partial derivatives with respect to x, y, and z.
It'll be the normal vector.
Right, it's just right. One, like, partial derivative with respect to x is one, partial derivative with respect to y is three, right? And partial derivative with respect to z is -1. Is that okay, everyone? Is it making sense? But is this like a random vector? No, this is exactly the normal vector of the plane, right? So the normal vector of the plane is 1, 3, -1, which is a gradient, right? And that's not a coincidence because what I'm going to write next is that the gradient continues to be before the gradient was perpendicular to the level curves. Now the gradient is perpendicular to the level surfaces. So when you have a level surface, the nice thing about the gradient is that it's perpendicular to them. So for example, maybe the gradient, actually the gradient will look like this in this case. And the gradient will look like this in this case. And that's kind of like the key insight because that's what will allow us to find like tangent planes to a surface. So let me write that down. So the first, like the important fact, like here, like the two important facts. So if you have a level surface, which again, let me draw it. So maybe that's what a level surface looks like. Then just exactly for the same reasons as before, the gradient happens to be a vector perpendicular to the level surfaces. Okay, so the gradient will look like a vector of this sort. On the gradient, the vector orthogonal to the level surface. Okay. And so why is that useful? Because, you know, when you have a curve, you want to find like a tangent line. That's where you calculus, you know, we have done this like a couple of times already for curves before. But when you have a surface, what you would like to find is a tangent plane. I think I mentioned this like the first day of class. So if you have a surface, like imagine that there are all these tangent planes. Right, to the surface, like that just, what is a tangent plane to a surface? It's really like kind of like the plane that approximates the surface most closely at a given point, okay? So you can use this to find the tangent plane to a surface, so let all of these represent tangent planes. Because what do you need to find a tangent plane? To find a, oh, sorry, what do you need to find a plane? To find a plane, you need a normal vector, right? And the idea is that you can use the gradient as a normal vector to the plane. So I'm about to do an example to make this a bit more concrete. So to find a tangent plane to the surface, you use the gradient vector as the normal vector of this plane. You take the gradient of f to be the normal vector to the plane. Or of the plane. Or in other words, what I'm trying to say is that the normal vector is the gradient. Okay. Let's see if we can do an example or two about this idea. Okay, let's see. Let me see if I can show you this first, and then I'll like do the. Okay, this one is actually kind of cute. So let's. This one shouldn't be too bad. I'm going to take, I'm going to take this level surface. So like the function is like xy minus yz plus z squared, right? So that's my function of three variables, and the level surface is going just to be, take the function equal to the value 3. So I'm going to look at all the spots where the function takes value 3. And so if you plot that, notice by the way that this is like an equation, like if you try to solve for, like, you could try to solve for z or something like that, but it's kind of like messy because it's like a quadratic equation in z. And one of the one of the coefficients is y. So the philosophy when you look at an equation like that is not try to write one of the variables in variables, one of the variables as function of the other variables. It's just like to leave it as it is. Okay. And if you just plot it, you get this cool thing. Okay. So it looks well. I mean, what does it look like some sort of like cone that grows inside, but well, I don't think cone is the right way to word here, but like, you get like a nice shape. And we're going to try to find the tangent plane. So what is a point on this surface? Let's see, one I could get one, I think, let's see if this one works. Okay, let's see, I'll take z equals 1. I don't know if you can see it, but there's this point, there's this point 311 that is on the surface. You have to kind of like look at it from the right angle to see that it belongs to the surface. How do I know that it belongs to the surface? Essentially because if you take like these values, you get 3 times 1, that gives you 3, and then minus 1 plus 1, right? So it's 3 minus 1 plus 1, that's 3. So that's why it belongs to the surface, because it just satisfies the equation of the surface. So what I'm going to try to do is find the tangent plane to this point on the surface, if that makes sense. So let me write all of that down. So the equation is it was x1 minus yc. Okay, so that was the function, and then we're looking at the level surface. Okay, so the problem would be to find the equation of the tangent plane at the point P. So find equation. P equals 3, 1, 1. Okay. And again, like the picture is like, no, maybe you have this, I will try to draw something similar to what's on the animation. Okay, so maybe that's how the surface looks like. And then there's this point P, which is on the surface. There's a tangent plane to this point on the surface. And what I'm saying is that the normal vector is the gradient of the function. Is that making sense? Okay, so what is the gradient of this function? So for that, you need like the partial derivatives. The partial derivative with respect to x is y. The partial derivative with respect to y is x minus z. Right? And the partial derivative with respect to z is minus y plus 2z. Okay, and then you want okay, so this is a formula that gives you the normal vector at any point on the surface, right? So this formula works as the normal vector at any random point of the surface. We don't want the normal vector anywhere. We just want the normal vector at this particular point, 3, 1, 1. So essentially what you want to do is evaluate the gradient, you know, at that particular point to get like the normal, that specific normal vector. Otherwise, it is like, you know, like just like a function that a vector that is, you know, is unspecified because like it does depend on the particular point how it looks like. So what is this? So you just replace like YZ, XYZ with those values. So Y becomes 1, X becomes 3, Z becomes 1, and then you get -1 plus 2, right? And so the vector ends up being 1, 2, 1. And so what I'm saying is that that is the normal vector at this particular point. Okay. Is that making sense? And that is like, and this is literally the, like, you know, the coefficients A, B, C that we always saw in the equation of the normal vector. So the equation of the plane writes A times X minus X naught plus B, Y minus Y naught plus Z, Z minus Z naught equals 0, right? Like, there was another way to write it if you move all the stuff with X naught, Y naught, Z naught to the other side. So A, B, C is 1, 2, 1, 2, 1, so you get 1. X minus X naught. X naught is, you know, think about this as P naught if you like. So plus 2 Y minus Y naught, which is 1, plus 1 Z minus Z naught. So Z minus 1 equals 0. And now at this point, it's kind of like your preference, how much you want to play with the coefficients. And I can write this as X minus 3 plus 2Y minus 2 plus Z minus 1 equals 0. So if you like X plus 2Y plus Z equals 1. So this gives you -5, -6, right? You can you just get -6, which becomes a 6 when you move it to the other side, right? So what I'm claiming is that this, and I'm about to plot it on the GeoGebra, but that will be the plane that's tangent to the surface. Is that making sense? Okay, so just to show you how that looks. What was the equation? The equation was X plus 2Y plus Z equals 6. So when you put X plus 2Y plus Z equals 6, you'll see like, okay, so the tangent plane ends up being this plane. Oops. So if you are to zoom in, like, you know, if you start zooming in, the idea is that the difference between, you know, the difference between the plane and the surface like becomes smaller and smaller as you zoom in more and more. So the tangent plane, you know, it is kind of like the piece of paper that best approximates the surface at a particular point. Just like the tangent line is the best piece of the best line that approximates a curve at a given point, if that makes sense. So like, you know, tangent plane doesn't mean that you can only touch the surface at a single point. That's like, you know, same way, because in the same way tangent lines can touch like a curve at multiple points. What matters is only the near the point where you're finding it, that like that is kind of like the closest line or closest plane in this case to the graph of the function. Does that make sense? Questions about this? Okay, so that is like for now, for us, that's kind of like the biggest application of the gradient, which is the, which is it gives you a vector perpendicular to either the level curves or the level surfaces. It's just that in the case of curves, we already had like different ways to find equations of tangent lines, so that's less useful. But this is really like the first time in the course that we find like the equation of like a tangent plane. So that's kind of convenient because of that. The other application, so as I mentioned, like so next week, I guess is the last week before the spring break. So the last, I think like the last things we'll do before the break is on Monday, we'll talk about critical points. So, like what is like a critical point in this case? What's like a max, a mean? How do you classify those? And then on Wednesday, we'll do the branch multiplier, which is a little bit tricky method. That's kind of like a tricky part of the course. But just since those are two different topics, let's end here today. And then on Monday, I'll tell you about like kind of like what the second derivative test is in our context. Okay, so I'll stop here and I'll see you Monday, if that sounds good.